Welcome back to another video on differential equations. I'm back with another lecture. This time we're going to be talking about non-homogeneous equations and the undetermined coefficient method. So let's get right into it. So first and foremost, we're going to talk about the non-homogeneous differential equation. And so a non-homogeneous DE is in this beautiful form where f of t is not equal to 0. So obviously the left side is the function with its primes, and then on the right side is just some function with respect to t. And so what makes this non-homogeneous is f of t must not be equal to 0. And so a solution to such differential equation has the form of y is equal to y of c plus y of p, where y of c is the general solution associated to the homogeneous version of the equation, and y of p is the particular solution to the non-homogeneous equation. And we know how to solve a homogeneous equation. We talked about it in the last lecture with solving homogeneous equations with constant coefficients, so that part is easier said than done. So all that's left for us is to find the particular solution. And so how will we solve for y of p, or our particular solution? This is where the method of undetermined coefficients can come into play. The methods of undetermined coefficient can help us solve for our particular solution. It's not always 100% the case, but for most cases we can use this method to solve them. And so what we can do is we can take a smart guess to create a general form of our particular solution, and that just pretty much leaves us to finding the exact equation. So a general approach to this is, one, we have to make sure that the function f of t is a linear combination of finite products of the functions for a polynomial in t, an exponential function e to the rt, or in sine of kt or cosine of kt. And so if the function is in either of these forms, we can use this method. If it isn't, then we have to find some other way of solving this particular solution. Now, to actually solve for our particular solution, there's kind of like a set of rules to follow, or not to follow, that can actually guide you to picking the right form of the solution. And so the first one is pretty much if there are no terms in f of t or of its derivatives that satisfy the associated homogeneous equation, then we can let our particular solution be the general form of f of t with its derivatives. So what I mean by that is, let's say we have a function, an ODE, in which its homogeneous version of the solution is c1 e to the t plus c2 e to the 3t. And our function is f of t is equal to 3t cubed. Then because 3t cubed isn't part of yc, then we can let our particular solution be at cubed plus bt squared plus ct plus d, and then that will be our general form for this solution. Now, this is not always the case. There will be some cases in which the function looks similar to one of the parts of the homogeneous version or homogeneous solution. And so this leads us to our second rule. So if f of t is in the form of pmt e to the rt times cosine kt, or pmt e to the rt times sine of kt, where p of m is a polynomial of degree m, then we can let our particular solution be t raised to the s multiplied by pm of t e to the rt cosine of kt plus rm of t e to the rt times sine of kt, where s is the smallest non-negative integer such that no term in the particular solution duplicates in the yc solution or yc equation. And so again, this looks kind of tedious and let alone intimidating, but an example is, again, let's say we have a new ODE, which is pretty much the same. The only difference is our f of t is actually equal to 3e to the t. Then we can see that 3e to the t is a form of c1 e to the t. So our particular solution will be a e to the t all multiplied by t, since that is the smallest non-negative integer that we can multiply. That will guarantee that there won't be a duplication in the homogeneous portion. And so once you established your guess, you substitute the equation into the original ODE and solve for the missing coefficients. In other words, you start taking the derivatives of our particular solution and you just plug it into our ODE that we were given, and that will help us solve for our missing coefficients, and then we can just put our y of c plus y of p together, and hence getting our solution to the ODE. And so that's pretty much it for this lecture. We're going to do some examples. Of course, we're going to have both cases and as well as calculating particular solutions. So other than that, I'll see you guys in the blackboard.